Okay, now that you've had a chance to try them yourself, I'm going to go over the answers for you. Looking at this first diagram, we have a rock hanging from a string. This is a piece of string, this is a rock. So it has a force of gravity. It also has a force of tension, and those are the only two forces in the diagram. And since those forces are equal, I'm going to draw two congruency lines, and I'm also going to label my forces, tension and gravity. Okay, next one. Rock is not moving, but it's resting on an inclined surface. So first of all, force of gravity, a force perpendicular to the surface because it's resting on a surface. The rock would like to go this way, but is being held back by the force of friction, so I'll put that on there. And there are no strings, so there is no force of tension. This is Fg, Fn, and Ff for friction. Okay, next one. This is a rock being supported by two strings. So, again, near Earth, so it's a force of gravity. One along here, and one along here. The angle to each of these strings is equal. So I'm going to put congruency lines on these two forces and label them. This is force of gravity, force of tension, force of tension. So you can have more than one of those answers being yes when you're drawing your diagram. Next, this is at different angles. So I have a smaller force here, and I'll have a longer force there. And this will be Ft. This will be a second Ft, and this will be Fg. Next one. This is a rock just sitting on a surface, very similar to the one we did on the previous page. So I'll have force of gravity, and I'll have normal force. And these will both be equal in magnitude, so I will use congruency lines. Now I have a rock being pulled again by two strings, so I'll have force of gravity, I'll have tension this way, and I'll have tension this way. Fg, Ft, and Ft. Now I have a rock, I have a rock resting on a surface but being held in place by a string. A lot of forces on this one. So I'm going to start with gravity. It's being supported by a surface. It's being held by a string. And it's also being held from not sliding by the force of friction as well. So I have four forces on this one. So Fn, Fg, Ft, and Ff. And now I have a rock resting on two different surfaces. So force of gravity is going down. This normal force for this surface is going in that orientation. This one will be perpendicular to here, so it'll be in this orientation. So we have Fg, Fn, and a second Fn. And in the last one, rock sliding down. Now it says frictionless incline. So it will still have force of gravity. It's being supported by a surface. There are no strings and there are no friction. So that's all you have for forces in this picture. Now we have just a few more of kind of different situations. Now these lines here are representing action lines like in a cartoon. So if we look at this one, the rock is falling and it says ignore air resistance. So I have a force of gravity, but that's it. Nothing else is pushing on the rock or pulling on the rock. Then in this one, it says rock is falling at terminal speed. That means, and you can see the lines are the same distance apart, that the air is slowing it down so that it's traveling at a constant speed, which means it will have zero acceleration. So these forces will be equal to each other. And this is Fg, and air resistance is a type of friction, so we can call that Ff. Next, rock is sliding on frictionless surface at constant speed. So gravity is being supported by a surface. There's no friction and there's no tension. So congruency lines, Fn and Fg. Rock is slowing down, very similar to the one we just did, but this time we're going to add friction. So I have Fg, Fn. The rock is going this way, so friction will resist it this way. These two forces will be equal in magnitude, so I'll use my congruency lines and label my forces. Okay? Rock is tossed through the air. It's an easy one. Only one force. No strings, no surfaces, so no friction, no normal force, and no tension. Rock is tossed through the air again. So again, gravity. That's all we have. Now in this next picture, there's no surface. It's being pulled horizontal, sort of at an angle there through the air. So we have gravity and we have tension. Fg and Ft. And in the last one, rock is being pulled upward. So if I'm pulling it upward, I'm going to pull harder than gravity, so this arrow will be longer. This is Fg, and this is Ft, because we're pulling along a string. Okay, now if we go back to the previous slide, we just want to look through each of these diagrams and figure out whether or not the rock is accelerating. Now by looking at the diagram, you can tell if the forces are balanced, the acceleration will be zero, and if they are not balanced, there will be a net acceleration, which means the rock will be speeding up or slowing down. So in this first one, we can see the forces are balanced, so the acceleration is zero. In this one, it's a little tough to look at by just looking at the picture, but the words give us a little hint where it says the rock is not moving. So if the rock is not moving, the acceleration is equal to zero. So these at an angle must cancel out this one. So if I were to draw the other sides of this triangle, the force of friction would be equal to this piece of this force, and the normal force would be equal in magnitude to this piece of this force. Now here it's a little bit easier to see. It's also hanging stationary, so not accelerating. The vertical part of these will cancel out gravity, And the horizontal part of this one will cancel out the horizontal part of this one. This one, same thing. So hanging stationary, so there's no acceleration. This one, two forces, cancel each other out, no acceleration. This, hanging stationary, so there's no acceleration. This one, holding in place, so there's no acceleration. Also holding in place, so there's no acceleration. This one says sliding down a frictionless incline, so we finally have an acceleration. This will be speeding up going down the hill. Alright, let's look at the other three. Here, rock is falling, ignore air resistance, definitely accelerating as it's falling. Rock is falling at terminal speed, these two forces cancel themselves out, so there's no acceleration. Here, sliding along a frictionless surface, again, no acceleration. This one, rock is slowing down is an acceleration. And rock is tossed through the air, we have an acceleration. Tossed through the air. Being pulled horizontally at constant speed. So part of this force is counteracting gravity. The other part is pulling it this way. So those forces are unbalanced. So that would cause an acceleration to the right. And rock is pulled upward. So this force is longer than this one, so that will be an acceleration.